Hello, everyone. Good afternoon. My name is Annemarie Luik, and I'm an assistant professor at the Department of Epidemiology. I'm talking instead of Arfan Ikram today, who's at the same department. My background is actually not in human brain mapping, but in psychiatric epidemiology. But I try to make or convince you from that this is actually still very helpful to you all. So. Let's see. Yes, this works. So let me start with the things I hope to teach you this afternoon. As said already before, I'm actually going to really focus on confounding. That's not because I don't think other things aren't important, but that's because I think confounding is very interesting and important in both big and small studies. Big studies offer maybe different ways to do something about it, but that doesn't mean we can't do anything about it in our small studies, which I think what I call a small study might be different than what you would call a small study. But I think a lot of you work in the sample size of maybe 40, maybe 50 people. So first, I will tell you about what confounding bias exactly is. Ryan already gave you the short recap, so you probably know already, but I'm going to repeat it and repeat it more slowly. How to determine confounders. So how do I know actually what is a confounder and what isn't? The difference between confounders, mediators, and effect modifiers. And lastly, I'll talk as well about how to handle confounding. As you can see already here that I use the epi terminology, but as Ryan again explained, this is matchable to terminology you're probably more used to. So first, confounding bias. And actually I'm not going to start with the definition, but I'm first going to convince you that it's really important to talk about confounding. And I think most of you will already know this and agree on that talking about confounding is. Because if you're determining a relation, confounding can lead to different things. First of all, the dependent variable being predicted by a variable other than the one studied. This means that the relation you are studying or you are seeing in your results is actually not the relation you wanted to study. So you see your result maybe that this relation exists, but actually it's predicted by something else. Second one, overestimation, underestimation, or even a complete change of the direction of the effect. So actually the sign is literally flopping from a minus to a plus, which obviously that completely changes your result, but even overestimation and underestimation can have quite large effects on your conclusions from your data. So confounding is really something we really want to keep in mind. Then obviously, what is confounding? Well, it doesn't mean anything else than that the effect estimate is distorted because there's a shared cause. And this is really important. Think of a confounder always as something of confounding that there is a shared cause. Because if you can keep this in mind, it will make it easier to determine what actually the confounders are you need to adjust for or need to think about. Because there's more ways, obviously, than just adjusting. So I will completely explain this with the use of diagrams. So you'll see this diagram grow and grow, and then I have to remodel it at a certain point because it doesn't fit anymore. But stay with me; it should all be clear. First, what is our question? Well, we want to, or our research question, we want to see whether this exposure has an effect on this certain outcome. Independent variable has an effect on this dependent variable. Again, I'll be talking about exposure outcome, but if you think about it as independent variable, dependent variable, that's fine as well, but just so you're aware. That is the association we're wanting to study. And then there's this other variable somewhere floating around. We don't know yet what it does, or how, when, whatever. When is this variable a confounder? Well, it needs to have basically 3 main rules, and you can kind of guess them, know them already, because again, Ryan gave the really short recap. I'm going to go through them step by step. So first of all, for a variable to be a confounder, it must be a risk factor for the outcome. So that means we have an association from a variable to the outcome. So that's, do I know how this works? Yes, that's this arrow there. If that arrow isn't there, you can't think of it, then it's not going to be a confounder per definition. Second one, it must also be a risk factor for the exposure, which you can see in this arrow. Again, that arrow not there as well. it's not going to be a confounder. If that arrow is there, but that one isn't, again, not going to be a confounder. These are like a checklist. So I can just have these 3 checks, like a risk factor for the outcome, yes. Risk factor for the exposure, yes. Okay, so then I need my 3rd check mark, which is it can't be an intermediate factor. That means that it can't be on the pathway. How do I do this? Well, then this arrow actually turns around. Now, the variable is not a confounder because it's the exposure affects the variable instead of the other way around. This is what we call a mediator, not a confounder, a mediator. So this is important to keep in mind. Obviously, when it's the other way around again, variable, we have, and let me check it with you. Yes, it's a risk factor for the outcome. Yes, it's a risk factor for the exposure. It's not intermediate. It's not going the other way around. This is what a confounder looks like. So if you think about your confounders, try put them in these like diagrams, like thinking like, do I have that one? Do I have that one? Okay. Sometimes people end up adjusting for confounders that aren't really confounders. They're variables, but they shouldn't be in the model, which obviously is something you don't want to do. There's something else as well, and this is a side note, so I'm only talking about this briefly, but the variable can also have an effect on the association between the exposure and the outcome. Again, that's not a confounder, that's a variable, and that's actually what we call an effect modifier. Again, I think in your field, and I have a background in psychology as well, so I was used to call this interaction as well, which is what you probably use. We also use it as synergy, which I think you tend to hear the least. So effect modification, the combined effect of 2 independent variables is larger than the sum of the individual effects of these variables. So it's not just A has this effect, B has this effect, and that's together the same amount. No, it's more than that. And this is quite important, although I have this on a little sideline here. It can be additive and multiplicative. Most people think of interaction as multiplicative. Factor A times factor B. That is interaction. I'm not saying it isn't, but it doesn't have to be. Interaction can also be additive. So keep that in mind that multiplicative is actually quite strong, because if you think 2 times 3 is 6, so it needs to be 6 at least. 2 plus 3 is 5, so if it's above 5, we can already think about an interaction to make this a really simple example. So the effect of the independent variable, this variable here, x, is thus not similar across categories of independent variable y. For example, the effect of neurodegeneration on cognition differs between levels of education. So if you're highly educated, the effect of neurodegeneration on cognition might be different than people that are lower educated. This could be from like more a brain or a cognitive reserve theory. They were afraid, didn't dare to come in. So if we're talking about effect modification, we actually often look at 2 groups and we compare those. So you can see here, for instance, this is the association between MI and brain infarction. It is different in the group of men than it is in women. So here you see even 7 compared to 4.6 of an odds ratio, but you see they're different. They're not the same. So you can that's clear interaction. And then lastly, about effect modification, because I was going to say this is just a side note. I'm only going to talk about this briefly, but I realize I'm talking about it more. I also wanted to emphasize that biological interaction is not per se the same as statistical interaction. We tend to test statistical interaction, which is whenever this joint effect of 2 independent variables is more than expected. This is the additive or this multiplicative effect. But whenever what we really are interested in or what we really want to know is a biological interaction. So whenever the occurrence of the dependent variable is dependent on the presence of 2 or even more, right? It can be 3 factors, 4 factors. It can be much more complicated because sadly research is never as easy as just 2 with a very straight line direction. So this is different. There's a difference between purely what you see in your stats. That doesn't have to mean it's that way as a biological field. So think about these differences. When you're thinking about your interaction term, think how it works. And that's generally what I would like to take you as like an overall learning goal. think about your models, think about the stats you're doing and what it infers and what you're implying or what it could imply. But just to keep that in mind, biological is not necessarily the same as statistical interaction. Much more to read about that. I was not as nice as Ryan that I gave some nice reference for you up to read on, but I can certainly look those up if you approach me later. Okay, back to what I was actually really going to talk about, which is confounding. Not for the last time, but again, I'm a believer of repetition. A variable to be a confounder, it must be a risk factor for the outcome, risk factor for the exposure, not be an intermediate factor. Just that. And with that in mind, I thought we'll do a little bit of quiz time. So I would like to have your active participation to make this a bit more enjoyable. So first, the study. I obviously had to come up with an example that had to do something with the human brain, hippocampal volume. And then because psychiatric epidemiology, I put some depression in to have a bit of my side there as well. So we're studying the association between hippocampal volume and depression. Or I say association, I should read Hernan's paper again and be less hesitant about saying some causal inference. But, oh well, we're studying this one. So we have this factor, job loss. Is this a confounder? And I would love to see hands. I give you 5 seconds to think about. That's maybe not a lot, I know, but who thinks this is a confounder? And can I please see hands for the people who think? No one. Who thinks it's not a confounder? Because that's the second. 1 person, 2 person. Oh no, we have more. We have a couple. Who doesn't know? Who doesn't want to know? That's... Yes, no, didn't see any hands on that one, yes. I would agree with the people who say that this is not a confounder because, yes, it has this, right? Job loss and depression are probably related. Job loss and hippocampal volume, again, I'm not a human brain expert, but I would say they're probably not related. So that's why I would say, nah, not a confounder. I have another one. Yes, number of children. And again, give your hands for those who think this is a confounder. It's not a confounder. I see some hands. I agree with you guys. This was a bit of a number of children depression. I don't think there is even a relation. Though you could say maybe it's a proxy for age, and an age is related to depression. I think it's getting a bit tedious, so no, not a confounder. Sex, we always see that everywhere. Who thinks this is a confounder? Yeah, I see some hands. Who thinks it? Nah, this is not a confounder. So definitely the audience overall, or at least the people who dare to respond, think that they respond for everyone, right? That's what I'm assuming. This is a confounder. So if you don't answer, be careful. So sex has clearly is a risk factor for depression. I think most of you will know that women are more likely to experience depression. Sex is also related to hippocampal volume. So we're going the right direction, already 2 check marks. And this does not seem likely to me. I don't think we first have our hippocampal volume and then. So no, so yes, I would agree with everyone that this is indeed a confounder. I have one last one, cognitive decline. Who thinks this is a confounder? I didn't ask that yet. They're too good. Okay, they're right. It's a mediator. Thank you. No. Again, it has the effect on depression. Cognitive decline and depression are related. Hippocampal volume, but... too quick. It's a mediator. I would say it's a mediator. Well, yeah. It's mediated. But so keep that in mind. So with your little graphs and your little arrows, you can think about it. Notice though, and I hope this might, on the one hand, not shock people in this room, but maybe it does. How many of you are doing like imaging marker research? Like how many are working with imaging markers? I assume quite a few. I see some nodding of heads. Thank you. I would say if you do imaging marker research, you actually want your research to be confounded. But confounding is bad. I don't want it. It ruins my results. No, you want it. Why? Think again about this one. As I said, I come back to my diagrams, this whole presentation. And we say the effect estimate is distorted because there's a shared cause. I'll give you an example. Imaging marker, dementia. we look at those associations, right? I think no one disagrees. Brain pathology. We want the brain pathology actually affects the imaging marker, because that's why we look at the imaging marker. It also affects the dementia. It's actually our hypothesis. So actually we use this imaging marker as the word says it, marker for brain pathology. So that's why most of the marker research is confounded. That's not a bad thing. It's a good thing. Otherwise we wouldn't be doing something meaningful. So the marker is an indicator of the disease or pathology of interest. It does not necessarily have an effect on the disease itself. If you think, for instance, one microbleed could be a marker of the status of the whole brain. We don't maybe expect this one specific microbleed to have a risk for dementia, but it might be an indicator of the status of the whole brain. So don't worry if your research is confounded. To a certain extent, you want your research to be confounded. That's the positive bit about this talk. It's not all bad. Though, then, I've cheered you up. Yes, confounding is good. But now I say real life, really, it's not that simple. It's never as simple as 1, 2, 3 arrows, 3 factors. It doesn't work that way. Or at least not in my research, and I kind of assume in no one's research. So I'm going to move around a bit, the diagram, just so that it fits all on my slide. But we still have exposure affecting the outcome. We have a pathology that affects both the exposure and the outcome. This is exactly as the one I've been showing you all the way around, except I've shifted the arrow as well. Brain pathology is there. These 2 arrows, this one and this one, imaging marker, exposure, dementia, outcome. Didn't do anything, no magic tricks here. They won't come as well, I'm sorry. So we have this one, we have the pathology, but then there's obviously confounder. But we tend to not have one confounder. There's usually more, and there's another one. And who knows, there might be plenty of more. And obviously, they're all related to exposure and outcome, because otherwise, they wouldn't be confounders. Then we have this, and then we think, oh, yes, this would be wonderful, but you already noticed I left some blank space on the right side, so I thought about more. There's mechanisms as well. So the pathology affects the outcome via a mechanism. And maybe there's not just one mechanism, maybe there's a second mechanism who does exactly the same thing as well. So this is more likely to reflect your study than obviously, and probably this is even too simple, but just to give you a flavor, we can up these things largely. So this is all wonderful, looking really great. And now we know this, and we know that sometimes it's not a problem, but often it might be a problem. So how do I then deal with this? Quite crucial. So there's design solutions. So the best way to deal with any bias is to make sure that the bias is never there. Avoid the problem before it exists, right? In general life, it's better to make sure that the problem just never appears than having to handle it afterwards. Generally, just less effort. So one of these is randomization. I all think you are probably very well familiar with randomization, where you divide participants in groups at random. I have a lot of happy participants. They're all smiling because my participants always love doing research. So you have this whole bunch of participants, all different people, and you randomly divide them, like throwing a dice into 2 groups. And look, you get 2 mixed groups. Some people will now look at this and think, yeah, sure, but I see something weird about these 2 groups. Because all the blue faces happen to end up in the second group. That's the problem with randomization. It doesn't work necessarily very well in small samples. Because randomized works in big samples. In small samples, you have the chance that everyone with, say, one of your risk factors end up in one group. So that makes it a bit more problematic, and you might need some more advanced randomization procedures. For instance, that keep in mind having a blue smiley face. Another one is restriction. And restriction means nothing else than restricting the admission into the study to a group of subjects who have the same levels of confounding factors. So, for instance, instead of including everyone from 0 to 100, you go to a smaller population. Which, if you again have those same people, this would mean, for instance, we only include the blue smiley faces. But then we lose a lot of other phases that we can't use anymore, which is, for one, a pain for recruitment, because your recruitment gets much more harder. It will limit your sample size. It affects external validity, because obviously these blue smiley faces are not representative of the whole group anymore. And you have residual confounding. What if there's another factor that's also, say, what if it's also if you are having, how can I say this, white eyes and a white smile? What if that was also something? In this case, it's fine because they're both in each group, but that could be something. Matching. So you match the groups on characteristics that are potential confounders. So again, our lovely population, 2 groups, and look, we make 2 exactly the same groups, so that we know that the confounders are balanced between groups. This is quite complex, because if you have one confounder that you know of that affects your association, this might actually be doable. Generally, we don't have one confounder. Generally, you have a lot more, and then matching gets really complicated really fast. Limits your sample size. You might not see it as well, but we're now missing some smiley faces from in our second groups. And it affects your external validity, again, because you're excluding people at the beginning. Residual confounding, you hardly ever know all your confounding factors at the beginning. We like to think that we know a lot, but it's generally quite hard. So yes, because you all liked it so much, we have another quiz time. Which design strategy would you use? You intend to run a small experimental study to see whether TMS has an effect on depression, including 15 participants in the experimental group and 15 in the control group. Which strategy would you use, assuming age and sex will be the most important confounders? A, randomization, B, restriction, C, matching. Who dares to answer, or shall I do an A and an ask hands? I'll ask hands. Who thinks A? No one's convinced about A. Who thinks B, restriction? I see doubtful hands, yes. Who thinks C, matching? See most people matching. I think, in this case, you can probably see that you would have, like, maybe some combination of matching and restriction. So this was a mean question of me to ask. Matching, definitely, like, matching on sex is quite easy, so I would say that's good, especially because here, in this case, sex might also be an effect modifier. I don't know that, but that could potentially be, because depression is so different in between these groups. Restriction, however, could be quite good for the age limit, because matching on age, again, if we have already a big sample, it's going to be there. So it's not always set in stone as well. That's why I put this in, because I don't want to suggest here that I have all the answers. I certainly don't have that much answers, to be fair. But you need to think about it. And thinking about these things beforehand can really, really help you. Just because this was a mean one, I put in a second one. The UK-Biobank, because we were talking about UK-Biobank, so I put that in, is designed to allow an intervention study, which doesn't happen much in cohorts. In part of their study participants, they want to see if TMS has an effect on depressive symptoms. Interesting. They have received magic funds, because it's quite expensive, I understand that, to do this in a group of 10,000 people. Which method would be best to divide participants into groups? Again, hands. A, randomization. Yes, I see some hands. B, restriction. C, matching. Yeah, I would say in this case randomization. If you go for these big samples, generally randomization works good. There's other things you have to do to address other biases, obviously. Blinding, which actually with TMS is quite possible for, like, for instance, your information bias. But this was just... However, we can't always do all of this, and sometimes we only realize when we have done our study already, or we're doing actually secondary analysis, or we use data that already exists, that we have to have some other solutions as well. Luckily, there are some analysis solutions as well, which one of them is stratification. I got really confused because this clock says something different than there, so I was like, I've only talked 10 minutes, poor people. You can analyze results per group. So as you see, this is actually the table I already showed you analyze it separately for men and women. And this can also be used for effect modification and interaction. This can be useful. It can be difficult or problematic with quantitative outcomes because this means that you have to split your variable. Splitting your variable, unless there's like clear validated cutoffs, is a perfect way to go for p-hacking. If you want to dredge your data, I'll first look at the tertile, then I look at the quartile. That doesn't work, I'll do a median cut. So that's why I'm always a bit hesitant. So I would say stratification in that case, do it as an illustrator. So show the results with just with the quantitative measure, and then use the stratification only to illustrate what you have found already. Then obviously multivariate analysis. We can do luckily something more in our statistics. And for that I go back to my diagrams. So this one I hope you still remember, and I would say you don't adjust for pathology. I think we can all agree because that's the cause we want to look for, so we don't do that. As you remember probably, we had some confounders as well who affected both exposures and outcomes. Yes, adjust for confounders, do it. So make these blue boxes, that's going to be the adjustment. Do that. The mechanism, in principle we don't adjust because that's what we want. We're looking at that. Though, if we have two mechanisms, and we want to single out a single mechanism, so we only want to know if it goes via route A and not if it goes via route B, then actually we do adjust for mechanism 2. Or if we were interested in mechanism 2, we adjust for mechanism 1. But think about what you really want to measure before you start adjusting for everything. It shouldn't be on the thing. It shouldn't be the thing you want to research. Multivariate analysis are, though, by no means the golden solution. They can't solve all of our problems, and they have some problems themselves as well. So that's why I think it's really important to interpret what fits and what happens in the model. When you do something, when you adjust for a confounder, see what's happening. When you adjust for 3 confounders, see what's happening. Because this will be very important when you're writing a paper, interpreting results. Be aware of overfitting, and this is probably more so in prediction research. But just putting in everything that you have is not working. There should be a theoretical basis. There should be some knowledge behind why you're doing this confounding adjustment. Loss of power, especially if you work in small samples, you might lose all your power and then you're not finding anything, not maybe because it's not there, but just because you don't have the power. Multicollinearity, when your confounders are really related, they can do really interesting things to your results that do not make any sense at all. So if your data suddenly is looking really weird just after adding this one extra confounder, look at the correlations between them. Multiple models in principle do not count as multiple testing, so don't be too afraid about that as well. Like you can, it's part of doing good statistical analysis as well that you look what fits there. So the summary. What is confounding bias? Well, by now I hope you all get very bored when I say that the effect estimate is distorted because there's a shared cost, and that this is due to 3 reasons: a risk factor for the outcome, a risk factor for the exposure, and not be an intermediate factor. Some people even get allergic to it already. I think that's positive. Confounding can lead to the dependent variable being predicted by a variable other than the other one studied, which, as said, in biomarker research, not biomarker, we're in imaging. Imaging marker research, this is actually sometimes what you want. Overestimation, underestimation, change of direction of the effect. And sometimes we have no clue which way we go around, and that is, again, very tricky. How to determine confounders? Well, I would say diagram. Draw them out, think about it, and really make sure before you start adding things at random, think this through. Difference between confounders, mediators, and effect modifiers, it's all in the arrows. So confounder, exposure that way, outcome that way. Mediator, from exposure to mediator. And, oh, this one disappeared. Oh, poor. There was a word here saying effect modifier. Effect modifier has an effect on the association. I did something wrong in my copying. Yeah, I'm sorry. I should have said which one. Well, it was a quiz. You knew my slides better than I did. How to handle confounding when designing your study. Think randomization, restriction, matching are some ways. When analyzing your study, stratification can help, so present your results between the confounder and multivariate analysis, but keep in mind, don't adjust for pathology, adjust for confounders. Don't adjust for mechanism unless you want to single out another mechanism, and interpret your models very well. Think, that's all what research is in the end. I wanted to introduce one last special case of confounding. We can potentially use confounding like this, but still, especially because all the discussions about p-values are so hot. So p below 0.5, is this exciting or is this confounding? Well, I don't know how many people really grew up with these tables yet, but I think most from psychology probably had these still, that you were calculating your own test statistic, and then you had to look up the p-value in this table, and if your t is large, you get a small p. So that means that this one here, the n, the sample size, if we lower, if that gets really big, this part gets really small, so that means we get a huge t. So in principle, if we can do a sample size that's infinity, we can almost get anything significant. Almost. Maybe not everything, but like a lot. So just remember that p is not only dependent on our effect size, it's also confounded by our sample size. So that's also why Ryan first said, like, we tend to like get rid of that p a bit and focus on the effect estimate and the confidence interval, because in this age of huge samples, it could be anything. So we have to look at this effect to make sure that this is actually meaningful, clinically meaningful, or any kind of meaning, pretty much. So that's how I wanted to end, and I was too quick. I'm sorry. But we'll go for a break, so you get 10 minutes more for coffee, which probably no one will refuse. Because
I think we could have time for the questions for the first couple talks.
Okay.
Let's
do that then. Who has questions on either my talk, Ryan's talk, Tonya's talk? Go.
I wanted to comment on something you said. So you're only going to see an effect if there is one. So otherwise, by the limit theorem, if there's no effect, it will go to zero.
I'm sorry.
The t-statistic will be normally distributed.
Yeah.
Under the null distribution. So
yeah.
As your data increases, you only have that problem if it actually isn't.
Yeah, but you're going to find like really small effect sizes are still going to be significant. So where, say, if you're
If they are positive.
oh,
As in, there will have to be an effect size.
yeah, there will be some kind of effect size, but it can be a 0.001. So then we can find a difference can be statistically significant for anything. And then so you get more into the question, what's meaningful? So often clinicians come to us and say, like, yeah, but this is I work a lot in sleep research, this is a 1 minute difference in total sleep duration. How meaningful is that really? So although that might be statistically significant, it's potentially not really that relevant. Yeah? Yeah. Yeah, so that's, yeah. Any other questions for Ryan or Tonya? Okay.
Question for you.
Uh-huh.
So if you have a confounding factor,
yeah.
and you have your exposure factor, so both are, we know there's some relationship between them, and sometimes in regression model we call it multi-collinear problem.
Yeah.
So I was just curious, do you have any, because if we put all them into the model, and certainly we're going to enter into some of multi-collinear
Yeah.
problems. So I'm just trying to understand how that could influence our.
So I think when you, yeah.
We are interested, right? How we.
When you have multicollinearity, it's, I would say, more a theoretical decision what stays in the model. So, for instance, if I would and this is a very famous example in epidemiology, when I would look for the effects of smoking on lung cancer. And I would put in carrying a lighter as a confounder. My result is likely to disappear. But that's not because carrying a lighter is that much of a risk factor. It is because carrying a lighter is directly associated, correlated with smoking, because the people who do that smoke. So in that case, it would be stupid, this may be a bit mean, wouldn't be very smart to add that one as a confounder. So if you're doing multicollinearity and you see, like, for instance, if you have it often with like socioeconomic status, income, like those tend to like all cluster together. I think either that way you choose what is theoretically most meaningful, or sometimes you can combine them into one factor as well. But I would go for a theoretical basis then to the decision, which can be hard. I by no means say, yeah.
This question kind of follows up on the multicollinearity problem. So in machine learning, we often have the problem that, like, say, for example, using a lasso regression, you have two variables that are very similar in prediction. Your lasso will choose at random.
Yeah.
Which one becomes a zero, and which one
Yeah.
will keep. And so people, like, they often use, like, feature engineering methods, like feature agglomeration and other things, to try and combine similar features into, like, features that are represented from multiple groups of features. In epidemiology, do you guys employ similar, like, strategies to sort of reduce the dimensionality of your predictions?
We do, yeah. Well, we have some. We do factor analysis in a sense. If we have like, say for instance, well, this could even be simple psychological questionnaire research, right? We can put in all 19 questions, or you can look at domains. So in that sense, we cluster them then as well, and look at the clusters, how they affect, and that is another.
Is that like the standard? Like it's standard to first approach it from the factor analysis, analytic, or dimensional perspective before going further?
It depends. Well, this is not a nice answer, but it depends very much on your question, actually, what you're doing. And this is why I keep on saying think. It depends on your question sometimes what you want to know. Sometimes I really just want to know if this one singled out variable is doing something. Sometimes I want to see it more as a factor. Especially for cognition, you can see this a lot, like a cognitive test, or should we have a whole cognitive status that. So it depends a lot. And this is, I would say, probably the most hard thing about thinking about all these things as well, that you can't say, okay, so if we just do this and this and this and this every time, it will work. No, because your questions change slightly every time. Your approach might change slightly every time as well, or maybe a lot. So that's, yeah, sorry.
I might just add really quickly to that. So when we're talking about prediction work, we absolutely employ methods like the learning methods that you were just discussing. So absolutely that takes place when we don't care about the effect estimates that we're looking at, where we just want to have the best possible prediction that we're doing. When we're doing more etiological work, then we're much more careful that we're selecting the variables, as Anna-Marie just said, in a very systematic fashion, thinking about the model and thinking about what fits in that sense of the room. With the factor analysis or the PCAs and things like that, absolutely they're applied. But one common critique we get when publishing these studies is that we lose a lot of the interpretation of what is the meaning of some factor score that you create after you reduce the dimensionality. But absolutely, that kind of that's done for sure. Yeah.
So follow up kind of both of those points. Thank you. So follow up to kind of both of those points is like one of the common things that's always been frustrating for me as like originally studying psychology and now doing more of this machine learning stuff is that parameter estimates are highly variable. So in this war vector machine or in a lasso or something, depending on what cross-validated sample you end up choosing, your beta values for your model can vary widely, and they can vary from negative to positive, right? So including 0, but nevertheless they're still included in the model. So in each significantly predictive model, it ends up choosing these features, but puts beta weights on them that can be a wide range of different beta weights. And I'm kind of curious, when you guys are building these, large models, and you're zeroing in on an effect size, are these effect sizes also similarly robust to cross-validation and bootstrapping and these other things? Are you able to develop that kind of intuition about how to interpret your model parameters? Because this is something that I find extraordinarily frustrating in machine learning.
You or I, either way. Okay.
One of the things, the models are not anywhere near as complex as what you're talking about. I think that it's orders of magnitude less complicated in general.
Yeah.
But so that in mind, when we see the effect estimates bouncing around a lot, that's a really good indication that we have a lot of what we call residual confounding. So whatever variable that we're using as our confounding factor, it's not capturing all of the confounding, and that there's lots and lots of residual confounding, either unmeasured, like you don't have a variable that you can add into the model that will address it, or you have the variable, you haven't entered it in the model, perhaps. Those would be maybe two of the scenarios. But with the learning stuff, I haven't done anything in that area yet. I hope to, but so I can't speak exactly. But that, at least how we interpret it in EPI, there's lots of residual confounding if your effect estimates are changing quite a lot. Yeah.
So we actually do quite a number of machine learning approach for looking at the large data sets. And in particular, you have large data sets of X and you have large data sets of Y. And often, if you use a sparse learning approach, then your results kind of becomes random. And what we often do is actually do a quite number of sampling approach, so then and repeat the study, repeat the analysis, many times, and we start to choose the ones from X. It's particularly, and that has to be reliable, selected for many times, and before you go for linking with your Y. And of course, that will make your interpretation relatively easier. Otherwise, you can go anywhere, to be honest. Lasso and all that stuff, you just get random results. It depends on your initial conditions, when you start for your estimation. So I think that's something I hope that people also do extensive kind of randomization and, the resampling this approach then before you really pull out your X to link it with your Y.